We are only proud of our accomplishments, happy that continued association with us. And one more thing that I want to mention is a unique blend of intellectual strength and spiritual wisdom. Now let me call upon Dr. K. Dura and the respected members, a very good morning to all. I am much delighted to introduce our well-known resource person, Ms. Govika Chakraborty. She completed her bachelor's from Gayatri Vidya Parishad College of Engineering for Women and master's from Andhra University. She began her career as an assistant professor at Gayatri Vidya Parishad College of Engineering for Women. Expanding her expertise into research and innovation, she worked as a research project manager at Jyfix Tools Private Limited and also worked as project manager at ShareSix and project and business executive at QLab Software India Private Limited. She is currently working at Quantum AI Global, initially as the interim COO and now as the head of innovation, where she leads transformative projects at the intersection of AI, quantum computing, and emerging technologies. Her diverse experiences from teaching to research and innovation make her an inspiring role model for both educators and professionals. Let's welcome her. And handing over the session.
CS and then GPC. GPC TSW. YouTube channel.
Hello.
ఇది మ్యాగ్నెట్ అనమాట. వెనక నుంచి పెట్టమని ముందు పెట్టు.
ఇంకొకటి అండి, ఓన్లీ గ్రూవర్స్ అని ఉంటుంది కదా, అది ఫస్ట్ ప్లే చేయండి. Okay, good morning one and all. I'm Gopika. Thank you so much for the kind introduction, most of which I have learned here, trying to implement outside in the industry. Teachers play a very prominent role, and I'm humbly doing my namaskars and pranams to one and all for the efforts that you're taking to educate the students of today, no matter how tough they are, the current students. So at that outset, today I would like to share a few things which even I'm trying to understand from the roots, right? When we talk about cutting edge technologies, frontier emerging fields, they evolve from the grounds of sciences. So today, if we talk about quantum technologies, we are celebrating this year 100 years of quantum theory, the foundations laid by giants. Back then, this year or maybe 5 to 8 years back, we are seeing some applications in quantum. Why? Because the infrastructure is developing. There is science, there is theory that has evolved. So science is based out of nature. Whatever you see here, as humans, we observe and then we derive why things are happening the way they are happening. and then we want to logically equate what we observe into some formulations, and then those formulations will become framework and will be implemented using some infrastructure. In this case, the hardware is currently evolving in quantum. So now, when we talk about quantum technologies, broadly this FTP is about computing, but there are other aspects of quantum technologies, which is communication, sensing, materials and devices. As materials and devices, basically the modalities behind a quantum computer evolve, we will see a more strong, resilient quantum computer. The current quantum computers are fault tolerant. We call the current era as NISQ era, noisy intermediate scale quantum computers, because the fault tolerant, that is error corrected qubits, are logical physical qubits, are not matching to the output that the current quantum computers are generating. Given this premise, how did the theory evolve so much back then? Most science is backed by strong mathematical frameworks and formulations, correct? Today, if we talk about quantum algorithms, specifically this session is about search algorithms, right? Let us broadly talk about quantum algorithms. I still remember when I got a computer, normal computer, the bada wala computer back in early 2000s after my intermediate. Mostly I used for watching movies and creating Orkut account. So I never explored what is behind the computer, right? I got a computer, there is a screen, there are some peripherals, and I'm trying to access it. Slowly after my intermediate, I joined computer science, and then C programming was there, and then some blue screen came up and they asked me to create some program and store it somewhere and retrieve it somewhere. In between, most of the times I'm getting errors, a lot of errors. And then I realized when I want to store something and retrieve something, I should tell the computer in the language that it understands. Correct? And that is a language that has been taught to me. Back then it was C language. Still, I don't know how a computer works, hardware works. All I am working on is the application layer. All I'm working on is to create a high-level language wherein computer understands in whatever language it is, which is binary, and then it will throw me the output that I want to see. Today, if you talk about quantum computers, even most of the people accessing classical computers today from any background, mostly computer science, electronics, mechanical, they don't really bother about, all they want is a configuration of a computer, right? How much speed, what is the storage capacity, is there any latency for my applications when I am working on it, which is high-end applications, that's all. But when I talk about quantum computers, and if I want to program a quantum computer, I should be a little bit cautious. I should be careful, because I'm not talking to an equal. I'm not talking to an equal, correct? Quantum computer will not understand the way I want it to retrieve information to me. Why? Because it is still evolving. The hardware, or as I told you, the modality is not yet fixed. So now what I think about is, if I have to get the best of the quantum computer. See, back then when I'm programming classical computer, I never thought about getting best of a classical computer. All I thought about is an application level. But today, I have to think, if I want to get the best from a quantum computer, what kind of algorithms should I implement? I still remember my teachers told me it all starts with algorithm, flowchart, coding, and then you get an output. Today, the first two parts are gone, directly coding. Whatever you say, it directly comes to coding. But in quantum computers, we are still in that algorithm phase, right? If I get the algorithm right, the other three parts have evolved. Flowchart will automatically come. There is the UML diagrams, whatever. Every part of the software development lifecycle has evolved so much. If I get the algorithm right for the hardware I am targeting, everything is taken care. Now, I am talking about a quantum computer. I am talking about a specific problem statement that I want to extract, that I want to implement on this quantum computer to extract some kind of efficiency out of it. So, what kind of problems are we talking about here? Search level problems. Okay, search level problems. Why is it difficult? I don't have to explain you how searching works, how sorting works, that is taken care. But when I'm talking about a quantum computer versus classical computer, in the context of classical computers, we immediately think of, even I, maybe 4 or 5 years ago, thought quantum computers is a magic. Whatever I give, it will give me because it is so powerful next to God, or maybe God himself or herself. Then I realized even gods need to be told what to do. And then I realized it is not the God that I'm talking to, it is the God within me that is trying to create a God out of machines. So the God power still lies within us, no matter how evolved the AI and quantum is. We have to tell it what to do. So if I have to get the best use of quantum computer in a search space, then I will use a set of algorithms. Fortunately, today for all of us, there is only Groovers, which is going the best case scenario. Who implemented it? Were they successful? Or is it a promise? Is something that we are going to see now. Correct? Searching, we all know searching, and why searching gets complicated and where the saturation happens in the classical systems. We all know that as much, just for example, we have one big campus here. Now just imagine we have twice of this campus and you need to find someone, and there are no linear paths. There are paths everywhere and you need to go to the best path. That is where it gets complicated if you don't have a supportive hardware. Correct? Here, a quantum computer comes into picture wherein it explores the best of the paths for a given algorithm towards a particular problem statement. This is proposed by Love Groover, which we need to be fortunate. He is an Indian. Okay, can I get the presentation, sir? Oh, still 1 minute. Great. Okay. May I help you?
Sharing screen.
Okay, you are sharing it with everyone.
Sharing it.
Okay, just share it here. It's okay. We'll see what happens.
Connects are also.
Avuna.
Hello.
Okay, while it is taken care, let me just. This one. ఇది క్లిక్కర్ అండి, ఇది పైకి వెళ్దాం. Done.
దాంట్లో చేస్తాను.
Okay. Okay. Before coming to this session, I had two things in my mind. I am not a mathematical person. I am not a physics person. Even I don't want to say I'm a computer science person, because computer science is not just coding. And today, most of the students or most of the people working in industry also, they are just focused on coding. I'm fortunate enough that I'm working in the area of quantum, wherein I have to see beyond coding. So I don't want to say when I come from computer science, but I know how to speak to computers. That's all, at a superficial level. So I had two options: to share with you the what of the concept, or to share with you the why of the concept. Usually the why is the mathematical derivations, the in-depth part of it. Why did Love Groover feel that he has to use this variable here and then deduce it in this way? Rather, I have taken the other path because I'm not qualified the first path. He is a giant, he has done something, and we, on the other hand, should start implementing and then build on it. So instead of why part, I went to what part. So what part is what happens when we understand this algorithm in the lens of a quantum computer. When a quantum computer is facing this algorithm, what actually happens? This is something that interested me, and this is something that I wanted to share with you all. Okay. What as in a solution to what problem is this quantum computing capable of? So when we think about quantum computers, let us not think about adding 2 plus 2 or 5 into 5, which classical computers are very good at doing. So what are those specific type of problems a quantum computer is good at? That is how, after the basis of quantum information and sciences, these algorithms. See, initially the basis was quantum information and sciences, then building on top of it was algorithms, and building on top of these algorithms are applications and software stacks. So Dutch algorithm is an example of a quantum algorithm that can solve problems faster by some measure than a classical algorithm. So usually when we talk about quantum algorithms, people just talk about Grover's and Shor's. But when I studied back then, this was also still the case. Yesterday I was discussing with my colleague also on this. So this algorithm was the first premise that quantum computers can perform the computing faster than the classical systems, but in a given measured space. The exploration of this algorithm did not see much of light today for reasons maybe we still need to evolve. But moving quickly to Grover's algorithm, this algorithm actually demonstrates the quantum speedup of complex to real-time variables that we're talking about. Yes. Idandi. Now clear? Okay, clear, okay. So while both of this algorithm show the potential, Grover's algorithm offers a wide applications method. When I say wide applications method, every computer has some space that it has to perform computations in. Every computer wants you to give options to explore the paths to get an optimal solution. Optimization is an inherent capacity that we need to extract from our algorithms, applications, and computers. So this is where Grover's occupies the bigger picture of the algorithms that has been proposed to solve on a quantum computer. So this is how, this is where we need to give credit to these algorithms, credit to Grover's algorithm, because it actually demonstrates a quantum speedup to be implemented on a quantum algorithm, a quantum computer. In this case, you may ask me, what are the proofs? Did we get a real-time speedup? Did we see such kind of speedups in real-time applications? I would say no, not yet. But if you take some toy problems, if you take some classical problems which run on classical systems and compare it with the same data set to be run on quantum systems, the time variation, the runtime, and the time that takes to actually run that algorithm is less, and the space that it takes to actually occupy is also less. Because we only have shallow circuits, we cannot have deep circuits in current quantum computers because it is NISQ era. You need to optimize it to fit the data onto a quantum computer. You need to move it on slideshow mode. Okay, when we all talk about a quantum computer, we immediately say that classical, we have a set of bit strings, and if we give the same set of bit strings to a quantum computer, it automatically, like a genie, takes all the inputs, it performs, it has some postulate called superposition, it immediately takes all the inputs together and throws you a best optimal solution as an output. This is what we have a assumption of. Even I was a little taken aback. This is the knowledge that I've shared from a beautiful YouTube 3 Blue Brown, I think. 3 Blue Brown, yes. I would suggest, if anybody is interested, please go there. It's just all borrowed knowledge that I'm sharing with you. So this has been also given in a few contexts which I've read in some papers, but this person beautifully explained why we need to, for some time, keep that kind of an assumption aside. That it takes everything together and automatically does some magic and throws you an optimal output. Keep that assumption aside. I'll tell you what should be assumed in a short while. But in a classical context, you have a search space, which is a set of values, and you're finding a number, a secret key. Grover's symmetric key, it actually helps you to find the best possible factors for a large number. In that context also you can see, but we can, for example, we can just at the moment call it as a secret key. Okay, let's say 12 is a secret key, and you have a function which is called as an operation, okay, which has a logic which takes all the values one by one, and when the secret key is hit to that operation, it gives you a yes, this is what you're looking for. Maybe in this case, true. Otherwise, the rest of the numbers, it gives you false. So the amount of time taken to reach to that value is something we're calling as a runtime. So these are the cases, how it works on classical, 0, 1 moment. Finally, you have a 0 or a 1 moment. Okay, how it works on a quantum. Before going directly into how it works on quantum, let us explore for quantum, if you have these 4 runtime values, immediately when I say this is a set of values which run on a quantum computer, I would immediately say what? Big O of 1, because it just linearly takes and it has a constant value, after which there will not be any kind of a speed up. Quadratic speed up, that is what is offering. Even Stanford, when this quiz has been given to a Stanford set of students, they answered as it is big O of 1. So big O of 1 is what? Linear to the array of the values that you are sending to a operation, in this case f of n. The rest have a different kinds of values. Now let us see what is the answer. Most of them have chosen, 54% have chosen the option D. 18% have chosen option A. In this case, the answer is option A. If you have, say, for example, 10 lakhs of values, if I have to do half of it, which is 5 lakhs, that would be my search space for to get an optimal value. That is a value that I would get at the half of it. If I do the root n of it, it will become automatically, it will come down to automatically a very less amount of what I have assumed to be done, that is 1000, root of the whole values. This is what we are talking about Groovers at the moment. So most common answer is wrong when you talk about a quantum computer, but the answer which is less taken is actually right when you talk about Grover's algorithm implemented on a quantum computer. Okay, so discovery is a promise. In this case, Groover has given us a promise that we'll have an unstructured data set, we'll have a set of values. On this unstructured data set, instead of getting an n by 2, we will have a root n, that is optimally getting the value that you're searching for. No matter how fast the runtime is increasing, no matter how unstructured your data is. So this is the promise. A discovery is always a promise which is recorded in our science or theory. How do we explore this? Okay, initially I told you, keep that assumption aside. What assumption aside? I told you quantum computers would make everything exponentially faster. No, not everything exponentially faster. Only few problems it makes exponentially faster. If you try to solve one problem on a quantum computer and a classical computer, we may be surprised that classical computer actually performs efficiently in getting the output rather than a quantum computer. Do not get discouraged, because quantum computers are meant to work on par with classical computers for most of the hybrid kind of problems today. If you see even variational quantum eigensolver as today, which we are using for drug discovery, finding the lowest Hamiltonian energy state, they do work in parallel, even in optimization problems also. We need to know what is the right set of problem that we need to break down and give it to a quantum computer. It is upon us to do the onus. So some very special problems are solved. For example, you have a large number. You have a large number as your key value. You want to break it. You want to find the prime factors of it. Now, in a given time on a classical computer, is it possible? Yes, is it possible? But unfortunately, the lives of whoever sitting here would be extended. Correct? We don't have an extension. We have a specific range for it. But if you give the same value to a quantum computer, let me again tell you, faulty quantum computer, fault tolerant quantum computer, that means error corrected quantum computer, if you give the same value, the factorization of the value, that means the prime factors of the specific key, can be found out in a specific amount of time. These are the kind of problems that we are talking about. Okay. What kind of problems are we talking about? Having huge search space. It is good not to have the number like this horizontally, but when you have a high dimensional space, this is where even our machine learning to artificial intelligence, the evolution happened. You have a higher dimensional space. Every time there is a new algorithm that has been proposed in ML, the dimensionality of the data is getting increased radically. That is why you need to have dimensionality reduction, and then even after dimensionality reduction also, if your data is not sitting well with your current infrastructure, classical computers, that is where quantum computers will come into picture. This is a very important differentiation. People who are trying to work with QML, if you have students, scholars working in QML, before even getting into the pros and cons of QML, we should first work out what kind of data that we are working out with. Even after reducing the data, the space of the data values that we are sitting on the current dimensions, SVM for example, support vector machine. If you take the data into a higher dimensionality space, the density matrix multiplication gets huge, which the current infrastructure may not be able to handle. That is where you bring in a extra added advantage, which of HPCs or then quantum HPCs. Here in this case, the space of the library or the space of the values that you're trying to find is getting huge. So the space is, search is large, search number is large, the space it is occupying is big, and the time taken to retrieve the key value, retrieve the value that you're looking for, secret key or whatever, based on your application, is also huge. So what is the solution here? Okay, how exactly those kind of problems look? Sudoku. Okay, in the papers we used to solve Sudoku. Now just imagine the dimensionality of the Sudoku getting increased. It is no more 9 by 9. We have a bigger Sudokus, and the probability of this 9 checker having the numbers which are not repeated in the adjacent also gets bigger, right? I think this is 60 power 9 or 2 power 60, I don't know. So this is Sudoku or graph coloring. Graph coloring is what? The adjacent should not have the same colors. The famous key factorization, the famous example here. These are the kind of functions that we are these are kind of applications that we are looking at to take help of a quantum computer, to take help of an algorithm such as Groover's. So these are NP problems. So basically, you will have a answer. You will have an answer. It's not that you don't have an answers for this. You will have an answer. But will you be able to verify this answer in a given amount of time? Is the question. Correct? So these are the problems that we will be able to solve. That's what I'm saying. I can just do some solution and leave it and my lifetime is over. It will get solved sometime, but that is not what matters, no? In this period of time, in a given optimal time, that has to be solved. So this is where we have a genuine bona fide quantum algorithms, which is, I really like this word, minimum viable path to see a genuine bona fide quantum algorithm. Why I love this sentence is minimal viable path. See, the power of a quantum computer, the power of these algorithms that are executed on a quantum computer, you and I cannot sit and derive it. No matter how big they are, we will not be able to understand. One point we will lose track. Correct? The session that I'm taking today, the specific set of problem that I'm going to explain today will have a minimal viable path. That is, I'm not going to show you the 4D, 3D levels of the dimensions. Still, I'll be able to show you because this person has graphically demonstrated it. But we're going to work on two-dimensional, where we are going to take the values, we are going to give it to this algorithm, we are going to run it on a quantum computer, which the implementation part also will come, and then we are going to see how it is actually extracted in a given amount of time. This is some space. Let us say this is some space. I don't want to use words like Hilbert space. No, this is some space. Okay, this space is like what is Kalpavruksham. Okay. Whatever you ask, it will give you. So how much ever you data put, it will take. Is it a good thing or a bad thing? Good thing, wow. Good, sir. What is the other side of it? A coin. It's always two sides. Profit, loss, happy, sorrow, misery. So what is the other side of it? It can take. But when you want something out of it, it's on you, no? You have put it inside. Now you have to extract it. Okay? So it will take an amount of values. Also, I don't want to use at this point in time, but it also takes, it is a complex plane, real plane and a complex plane, which we usually don't see in the current classical systems. So it can also take real numbers, it can also take complex numbers. That is why Hilbert space is so evolved. This is what I'm going to discuss in next phases. So if you have two states, the probability of getting this and the probability of getting this with this values, at this state it is 97%, at this state it is 3%. What am I trying to explain here? I don't want to derive how this is, and I don't want to do it root and say the modulus of it is equal to 1. All I wanted to tell you is quantum computer works on probabilities. Okay, you have n number of data, 2 power n states would be generated, and this 2 power n states would actually be sitting on a quantum computer in form of a circuit that you actually design with some operations which are gates, and these values will be manipulated according to your desire, to your problem statement, in this case to find the value secret key, and you get a value, correct? It is not so straightforward. It basically gives you the probabilities of having a value x, of having a value y. I don't want to use x, y, z because they are what is this? I would like to use probability of having a value a, b, c, d, e, and so on z. Whatever it is, it will give you the probabilities. Okay. In this case, the probability of having this is 97%. So when do I know that? When I measure it. When I measure it. What is this measurement? Normal physics measurement. You have a unit, you will measure, and then you'll get a value. So then I'll measure this, I will get a value. Okay. Then I will have to decide, is this something that I am looking for? If not, you repeat it. You increase the repetitions and you continue the cycle. Okay, I told you, please let us get out of that impression that superposition, something magic is happening, because we are going to unveil that magic today, no? Classical, you have set of bit strings. If it is 2 power n, you, for example, n is 8, n is 4, n is 2, 2 power of n, and then classically, you will have 1 by 1, 1 by 1, 1 by 1. Quantum, automatically everything goes.
Actually, YouTube is doing. No?
Okay, okay.
That is different.
Oh, am I seen on YouTube? Should I say hi?
Yes.
Now voice loud, but everyone
Yes.
Correct, correct. Yes. Okay. So let us see beyond parallelism. Okay, yes, parallelism is the inherent property, but let us see beyond it. If you keep on appreciating things, we will not know how the things are working the way they are. So let us cross it off for some time and see how actually it is happening, or if it is happening the way we are told that it is happening. Okay, this is the beautiful thing that even I have discovered lately when I was learning about this groover thing. Why I had to learn is because everybody is talking about groovers. I only know basics of it. I wanted to learn some more. Where is this abstraction coming from? As I told you initially, I was talking about classical computers. I don't know how those chips are made. I don't know how actually assembly language, people work on assembly language. Back then, maybe a few microprocessor lab I have worked on, but actually there is a hardware. To our surprise, there is actually hardware in that sleek laptops or a sleek phones. And that hardware has a set of programmable chips, correct? Which is working in tandem with each other. This hardware of classical has evolved so much. It is getting some kind of signals, switches, 0, 1, 0, 1, 0, 1, based on which it will have set of bits, based on which there is a integer or a text alphabet. If you go from top to bottom, I have a number, I want to store it on my system. the system will convert that number into a binary set of digits, and then that will go and sit. However it is going to sit, I don't know, because I am not designing the hardware. I know it will sit. I know it understands only binary, and I have a number or an alphabet, ASCII or an integer. It has something. Let us go to this side of it, which is quantum. This ket representations, I think by now, it is for us to understand. It is quantum and classical. So there is a data type, which in this case an integer. It has set of strings which is converted then, and the layers of abstraction comes here. Whatever the magic that we are seeing, entanglement, superposition, parallelism, so much is happening. The magic comes from this part. The randomness comes from this part. Correct? Unfortunately, there is no magic here, because when the magic was happening, I was not born. That is why maybe it is not magic for me. I took it for granted. But the actual magic today we can see here, right? How the bit strings, how the values basically are being generated randomly, actual randomness. It's not pseudo randomness. It is actual randomness, how it is being actually generated. And every time it is different. Mind you, every time it is different. Every time I can actually manipulate it. Every time it will increase, amplify the probability of getting the best case scenario for me. This is my comrade in this case. So the hardware it is. Fortunately or unfortunately, this hardware has not been standardized as yet. We have a lot of options of modalities. But if tomorrow somebody says quantum is great, this, that, it's not the application layer of it. It is the hardware part of it. And behind the hardware is a science, which is quantum mechanics and the postulates. This session, we will see how, we will start with this part, okay? We will start with the middle layer part. And then once we reach to a certain point and we wonder, wow, what's happening? Then we're going to demystify and say it is nothing but the science, which inherently runs the hardware, which is quantum mechanics. Outside it is same. See, at the end of the day, you don't get a wave. You don't get particles, and you don't catch particles in the air, correct? At the end of the day, we get 0 or 1 only. But how they are getting processed, that is the magic which is happening. End of the day, when you measure, when it collapses, it gives you 0 or 1 only, correct? Focus on middle layer without hardware as of now. In classical, you have a state. What you see is a state. I have a number. I know the array size. I store the number, and that is static. I know the memory. I know the array size. I know, and every time I want to retrieve it, I'll give you n or n plus 1. If I give n minus 1, I'll not be able to retrieve it or store it, because it is the size and the array storage space is less. So just to add, when we were doing C programming, we didn't know how to work. So we used to initialize array to 100 or 500. The madam used to, why are you occupying so much of memory? Just in case, madam, we're giving big numbers. But I'm storing only 5 or 2. So that is where we understood later on optimization actually matters. You don't just initialize arrays to a bigger amount, because it is actually being allocated for you as a user. So optimization actually matters. Here in this case, when you allocate a space for a value, what you see is what is stored. Very important. What you see is what is stored. I see 1 is stored the way it is supposed to be stored. And it is there. Unless it is not, unless it is RAM, it is there. ROM, it is there. No, when you switch off also, it is there. Quantum in this case, the state is not what you see, because this is where it comes into picture. Qubit visualization part initially has been dealt, correct? So there is a space wherein you have the bits. It is bits, it is qubits. You have these qubits always being rotated or directed to a coordinate system, to a value which is more inclined to your desired problem. I would always want to focus on the desired problem. It is not magic that is happening. It is just that we are not able to comprehend it. That is why I'm telling why it is happening. We are not bothered. It is supposed to happen. But how it is happening, I am actually moving that. I'm actually moving that based on the algorithm that I have proposed. So this, if I get this string settled somewhere in this space, correct? X and Y coordinate, somewhere it sits. And let's see what happens next. Okay. Discrete value that is read out. Every time I read out from my system, every time I read out from my system, that means I measure from my quantum system, it collapses. It collapses. That means it should be either 0 or 1. That means 0 or 1. No, you don't see 0.1.1. You don't say continuous. You see a discrete set only. When it collapses, you have a value. Now we wonder if the same value that is there here, same value that is here, zeros and ones only, what is so powerful about it? This is important. Discrete values that are read out. You don't get continuous as an output. You always get discrete as an output only. Here it is deterministic, here it is random. The beauty of the hardware which we are talking about, the red things, I've taken photons because we're working with photonic systems. The beauty is in the randomness. The beauty is in this randomness. That is deterministic. You know, if I give this bit string, I will get this bit string as an output. If I have to again have an optimized way of getting it, I have to change an algorithm. Sorting algorithm, I used to always choose bubble sort. That is the only sort I understood or got it. But there are other better optimized sorting algorithms. Then I realized. Now, when it is random, every time you try to measure, every time you increase your repetitions, every time you give a different manipulation to a state vector, you get a random set of numbers. So now the question is it good or bad? Every time a new number string, is it a good or bad thing? Good thing. Why will it be a good thing in this case? In this case, why would it be a good thing? Because of this coordinate system, right? This, I think that will come, but I'll just say this. If two things I want you to take ahead in your, I want you to come out of this parallelism superposition mindset, because we are not appreciating quantum computers, we are trying to work on quantum computers. This is the key I want, correct? And this is where the state vector currently is lying. Ideally, the rotation should happen this side or this side. Ideally, if it were me, I would say this, because I already know this. Correct? This is where it has to go. But it will not know. Based on the randomness that is generated from the hardware layer, your middle layer chooses an angle to be rotated both ways. Once I know I am reading out a specific number, I am looking out for a specific number. Once the quantum computer knows this is the number, there is a formula for it in Groover's algorithm. That is how we will know this is the number that we are looking for. It will slowly try to increase the probability of your system going towards that number. This is the second part of Groover. First part is unstructured data. The second part is amplifying the probability of getting your value. So unstructured data is there. There is a key hidden in it. Then there is amplifying this value. Amplifying this value. That is, every time I make a measurement, every time I do a repetition, I want to go near to this. If I go farther to this, it is still not root n. It is again be n by 2. So if I want to go nearer to this, this is where it is random in nature. If it is a 4-qubit system, 2 power 4 possibilities of quantum states that I need to execute. That is 16 here. We basically work with Hadamard gate and 2 other gates that is present. Implementations will be dealt in the afternoon. Any algorithm, Shor's, Groover's, let us not worry about implementation. The code is there. Qiskit is giving you the code. We'll just execute the code. We don't have to manipulate anything also. In the best case scenario is already given by Qiskit. The best case scenario of executing this algorithm on this string size, n size, this is the output that you're going to get. It has already given. What we need to understand is when that algorithm is being implemented, how are the state vectors being manipulated? How is the coordinate system is moving? That is why I really appreciate this problem statement by Government of Andhra Pradesh. One is qubit visualization. It is very important for students, for anybody who's trying to learn anything. We are very visual people. As humans, we are very visual people, right? That is when you see quantum visualization, Qiskit Blocksphere, it is so visual in nature. Otherwise, I don't know. Classical system, I still don't know how it is working. It is retrieving and I'm happy in the application layer. Whereas here, I will know basically where it is going to, where my output is being redirected to every time I make a measurement. So here is where it is important to have visualization. What are these bars? These bars are nothing but the probability of getting that particular string. If I wanted this to be extracted from the set of values, the probability is higher, correct? And this is moving towards this. If I am here, that means I am towards this part, 0, 1, correct? 4 qubit system. Now let's see. This is the end of any algorithm that you try to implement here on Qiskit, because we're talking about quantum computer. This is what it is. Okay, it will give you a set of values. It will throw you the measure after you measure. Inference is a concept that in a quantum system you infer the probability of getting a value suited to your problem statement. So out of these set of values that are generated from your quantum computer, 11.5% is the highest, I suppose. Yes, 11.5%. That means this is my key. This is my key. This is the value that I am looking for. Is it yes or no? We have verification. Okay, quickly we can verify. I'll talk about that. Okay. This is what I want to focus on. This is what is seen outside. I have k number of values, 2 power k states will be generated, or n, whatever we can take. But implicitly something is happening. Implicitly a state vector table is being generated. Implicitly state vector table. Vectors are everywhere. I thought I'll escape, but yeah, unfortunately. State vector table is generated for each and every value that is going and sitting. Is this visible? It is not visible. If it is visible, what would I do? I would start manipulating it, no? It is not visible. Why is it not visible? Even the system does not know until and unless the randomness is generated. Every time the randomness is generated, one part of the value, if you see qubit visualization, block sphere visualization, every time a state vector, this is the hardware. Every time the randomness is generated from the hardware, the state vector is getting manipulated, which is being seen on this block sphere system. And finally, when you measure, you will get a output. So implicitly, some kind of calculations are happening based on the modality of your quantum computer. There is no one modality. You have superconducting, you have photonics, you have ion, multiple. Okay. Which one will win the race? Nobody knows yet. But as of now, photonics people are looking for. Neutral atom is also people are looking for. Okay. So this is where the genius, I told you. Now coming to the physical measurement. When I say I have measured here, when I said the application layer, what is happening? Something here is being collapsed. Something here is being collapsed. What is collapsed here? My qubits are collapsed. What I say is my qubits. The qubit modality can be any of the hardware. So probability distribution of all possible bit strings. Randomness stems from quantum mechanics. So from this randomness, the bit strings will be arranged. From this randomness, my value will be chosen. Remember the first example that we have given? Set of values 0 to n minus 1, 1 to n, 0 to n minus 1. So that is the set of values I want to search in, and the probability distribution of finding that key in the first half, middle, last. That is the classical system. But here, what I told you, everything will go parallel, superposition, Gini will come. If we leave that mentality, what is actually happening is, once you have set of strings coming into it, the randomness is generated and some strings are pushed. Maybe this is the value, this is the value, this is the value. Because how it works? The Sudoku thing, right? You have point A, you have point B, you have multiple paths. You have multiple paths going to, and some paths are blocked. So this is the path A to path B. This is finding the exact value. You find an optimal path. The optimal path selection is nothing but the randomness of choosing a path. You and I did not give the path. No, it is not K cluster algorithm. I'll give you K. This many clusters should be formed. I did not give any kind of preference here, except that I want this search to be at the quadratic speed with the root and possibility. That is all runtime I have given. Now, this randomness will probe to get the value out of the system, and that is also not exact value. Quantum computer is not giving anything to you on platter and saying this is what you asked for. No. we have to take a good look at it, take the probabilities of that values occurring, the highest probability, and then we go back and verify. If that is it, good. If that is not it, we have to do the whole thing again. So after reading out the value, the state of the system changes such that probability is now focused on value read out. So I have, initially we thought that this has the most probability of getting, and now this is the value. This is the value. Means, remember, we had a operation, function f of n, and the key goes into f of n. If that is the key that we are looking for, we get true. For all other keys, it is false. So the key is found. This is the key which we are looking at. Very important, delicate and sensitive probability distribution. It is not our general probability that it is a strong probability this will happen. Tomorrow this person will win. In this election, this government will come. We don't have strong data. We don't have strong output also in this case. All we have an assumption that this kind of data, which is unstructured data spaces, this algorithm actually gives me a quadratic speed up. Nobody has proven as yet, but mathematically proven, some small problems are being trying to solve nowadays. That is why it is still delicate and sensitive probability. The other reason is the randomness that we are getting. The randomness today, semiconductor, transistor, silicon chips, we have those, standards for the hardware. Nobody will go and try something new in classical systems because already standards are made, this kind of modality is working. Whereas in quantum, there is no fixed modality, no? Today I say photonics is good, tomorrow the superconducting is good, day after I say neutral atom is good, correct? That is why it is delicate and sensitive probability depending upon the randomness that is being extracted from the hardware. As we look, the probability collapses. That is again quantum postulates. When I look, when I measure, when I infer, the qubit collapses. Any qubit of any modality, it will collapse. 0 or 1 probability. Okay. This is where we are getting randomness. This is the state vector which is being generated. It is invisible. It is invisible. If after it got collapsed, after you measured, you can actually go back, write a small log program to your Qiskit quantum computer. It will give you all the state vectors that went into giving you a 0, 1, 1. Why 0, 1, 1 got the highest probability out of all the states, 2 power 4 states, is something that it will give you in what runtime. So this is invisible to us. It keeps on changing. I'll tell you the formula how it changes. So finally, what you see is only this much. This is what we are looking for. The question we need to ask is, I think origin spelling is wrong. The question we want to ask is, how did this distribution come? Fine, I got my value in quadratic speed up only, in root and possibilities only, I got my value. How did it come? Why again? I don't know why it came because there is quantum mechanics, that is how nature is. But how did it come? At least this quantum computer I know. State of the computer as being described by a big vector. The origin explanation is, why are we discussing Groover and not some rover or some other thing? Why only rover is not there? I just made up as a synonym. So why we are discussing this? The state of the computer has been described by a big vector. Okay. Current state. Currently I'm here. Okay. Everything is geometry. Currently I'm here. If you measure the length and breadth of this room, if you have a radius which is in center, if you measure how far I am, you will know, no? The lat long of the earth, all the Google Maps is working by lat long only. The lat long is abstracted and you find Rishikonda beach. But there is a lat long behind it, correct? So if I take a quantum computer together as a whole, it is nothing but a big state vector with some set of values. Those set of values are always probable towards getting to a certain output that we want, which is nothing but a big list of numbers, a number in high dimensional space. Any one you can pick. Any one you can pick. You can either say a big state vector, high dimensional space number, or a big list of numbers. Okay. Yes. So we are entering into the first phase of Clover's algorithm. There are two ways I have a second PPT also, which is completely mathematical. You have a Grover algorithm, step 1, step 2, step 3, step 4, step 5, how it collapses, Hadamard gate, how it works. I can also show that, but this is what I was curious about, which I've learned. What is a rhyme? Everything has a rhyme, no? You have a rhyme, I have a rhyme, the way we work has a rhyme. So what is the rhyme behind a quantum computer executing a Grover's algorithm? The rhyme is nothing but there is a function. This is the function. And the function is being run on a quantum hardware, whereas the magic is happening. And once the magic happened, it pushes the function to a value. There is a big library of numbers being created, which is nothing but state vector is being generated, which is invisible to us. We will not know what is happening. And there is some kind of computation being done, modulus operation, modulus square operation of each and every item. Each and every item modulus operation is being happening. I'll tell you why, because there is something called as flip. And there are set of value states, set of states, 2 power n states being generated, and the probability of having this state, probability of having this state, probability of having this state square. Okay, linear. This is the final thing. If I have to just see and tell, 0.25, 0.12, 0. This is the highest. If I have to see and tell, this is the highest, I will say. Correct? This is what I'm looking for. I just wanted to again tell you. State vector, you find the magnitude of it. In this block here, you find the magnitude of it, where it is standing. And then based on which you'll start rotating your sine theta angle. Sine and cos you will use. Why I don't know, but sine and cos are the angles that are being maintained here. If you go to this also, you can have one more angle, diagonal. So state vector, magnitude, you square it, and then you get a value probability of something happening in that particular time. In that particular time, again execute the whole thing, this might change. In that particular time, it is this. The onus is upon us to amplify the probability. That is the third step. Amplifying the probability of getting this key. That means rotating it to our desired location. We have a formula for it. This is what we are looking for. Yes or no is something that we need to decide on. As squares that in positive values, flipping signs play a major role in Grover's algorithm. Now you may wonder, there are some negative values also. There are some negative values which are being created implicitly, inherently. As I told you, for quantum, real numbers, complex numbers, both are taken into consideration. Bloch sphere or Hilbert sphere, it's a very huge, large space, correct? When we flip a sign, initially what it takes is, you have a you have a function here, some value is going in, some value is coming out. If it is key, you will have true. This is what I'm looking at. If it is key +1 or key -1, that is the value that we want before or after anything it is. Finally, you are getting false. Correct? This is what is happening in classical. Now, for Grover algorithm, after taking this, what happens? If it is true in general operations of classical, Grover algorithm flips it. Let's see. For visualization, scaling down to smallest possible case. 4-dimensional space is something that we can visualize on a Bloch sphere. We can understand. When we see the visualization of a Bloch sphere, there are a lot of tools. We can actually understand until 4D only. That too, it will get very complicated once you try to start multiplication. For the ease of understanding, let us scale it down to the smallest possible case, which is 2-dimensional in this case. So 0 or 1 possibility of getting state is higher, as you have seen. Moving forward, we'll have a state vector in this dimension only. Okay, so this is where the current magnitude, this is where the current state of the qubit is lying. On which axis this is? Is it fixed? Can we change? Can we change it or is it fixed? It should always be y. We can change, correct? It depends upon where you actually want to work with. I want to work in this region. I can change. I want to work in this region. So currently, is it at this region, which is both plus. Signs are very important here. Fourth step of Grover is flipping the signs. That's all. Fifth step, it is already over, Grover's algorithm. Flipping the signs. Let us see why flipping the signs is important. So this is where it is currently. That means we got the value. We were thinking this is the value, no? In our block sphere, this is where my key is. My current state is here. So every time I need to make a theta angle change, I will not make it towards, let us say I'm on X and this is Y. Okay, I will not make it towards this. I would like to make it towards this. Okay, you want Y? Okay, I'll give Y. Okay, it is always like this. Now, right. Assume we didn't still reach here. We are still here, right? When we are here, we need to calculate two things. One is the magnitude, the other one is the angle of rotation, which is sine theta. Magnitude and angle of rotation. Two things we need to work on. Assuming we didn't go to the final stage of it. Everything will be automatically calculated by the state vector, after which when you have a state, the probability of state will come. Two operations, root of x square plus y square, and there is a formula for sine theta, pi by 4 by 1 by root n. State vector movement in unit circles with a length of 1. Because we are in two-dimensional space, we were only working with x and y. This particular state will completely rotate at this angle. If I have no idea about how I'm working with, what I'm going to do is, I will initiate into a general constant, like how I initiated array 100 or 200 back in my days. I didn't know I have to allocate it some optimal space. I can randomly give some number and it keeps on rotating. Unfortunately, we don't have such quantum computers for days that we can get access to. So we need to be a little careful when we are trying to work with. That is why two-dimensional space that we have taken. 2 part 2. State vector stay. Okay, where does state vector stay? Before that, okay, I think state vector of movement. State vector, the focus should be on state vector. The focus should be on flipping. Groover algorithm. Number 1, initialization of unstructured data. Number 2, to find that value, we need to amplify the probability of getting that value. Number 3, the state vector movement is important. How it is moving? We are calculating an angle. That 5 steps, the Groover algorithm is there. When you're implementing, you will know. The state vector movement is important. Why the movement is important? Because your value is somewhere in the Hilbert space. You don't know where it is. Once you read out the value, you should see if it is nearer to the value or farther to the value. Based on which the state vector movement should be there. This movement, because it is 2D space we're talking about, it moves in a unit circle with the length of 1 magnitude. So where does it stay? Where do the state vectors stay? It stays in this space. Now this is quite terrifying for me. When I look at it like that, it can stay anywhere. No, it can stay anywhere on this. That's why immediately I scaled down to two-dimensional. Because we can think in length and breadth only. Once the third dimensional comes, some part of my brain is over. 4 dimensions, I'll not be able to imagine. If I have to understand something, I have to first break down. That is what we are good at, breaking down algorithm step by step, and then we consolidate. So state vector can lie on any part of it. That means the state vector, which is inherently, implicitly generated based on the randomness of your hardware, which can have any state as a final measurement, based on the probability of that state occurring, can lie on any part of this block sphere. Now, why did we choose this block sphere? We can have this also. Because it is easy to actually visualize. Correct? It is actually easy to visualize. But it is a Hilbert space. Infinite possibilities. We are only dealing with real time. Again, I've closed my doors to only real time. I'll tell you why only real time I've chosen for Groovers. If it is for Shors, complex numbers would actually make sense. But Groovers, we are anyways doing a square of it. So it will be positive for us at the end. That is why I've taken only positive numbers. I've taken all real numbers. I didn't venture into complex numbers. So the state vector stays on a higher dimensional unit sphere. Where does it move? It moves in the unit measurement of the circle, the movement. Where does it align into? The 2 coordinates, because it is 2-dimensional. In both ways, it was going to align. Okay? For visualization, we have scaled down. I think, am I going back? Yes, I'm going back. Yes. So where am I getting this quantum edge from? I'm talking about unstructured data. I'm talking about quadratic speed. I'm talking about having something in the runtime of root n. What am I talking about here? I'm talking about somewhere I'm extracting this quantum edge. You have a state in which it is 0 or 1. What do I observe at the end of the day? I observe continuous or discrete. I just told you before. Continuous or discrete? Discrete. At the end, in a classical system also, I observe 0 or 1. Now, this is the state. For qubit, what is the state? Go back to that slide which I told you, randomness versus deterministic. What you see is not what you get or what is stored. So it is random in nature. That means in this high dimensional space, based on my magnitude alignment of my coordinate system, it can lie anywhere. If I scale down to 2D, I will know it only lies in this plane. If I scale down to 3D, I don't even know how to draw cubes. I'm very bad at geometrical drawings. Or 4D, I don't know how to even draw. Okay? So, but visualization we can do that. This is what is beautiful Blocksphere visualization tools. Just Google it. You can just keep beautiful. You can just give inputs, number of qubits you want. It will just generate state vectors. It will give you states. It will create a circuit and it will show you a Blocksphere. Where is your current status? It's just for understanding. So the edge comes in this having a random state being allocated, and every time you want to get closer to the value, you need to actually amplify the probability of getting closer to your key value. Did I miss anything before? A unit vector. What is a qubit? A unit vector, in this case, a 2D space together with a coordinate system. Qubit, generally these days, what is a qubit? A qubit is everything between 0 and 1. No, qubit is basically a vector, a unit vector in the space which you're trying to work. Now we have brought on a 2D space together with a coordinate system. Coordinate system both have complex plane and real plane with perpendicular x and y direction without when measured. Here it's 2D x and y, otherwise it will be x, y and z also. Okay. Yes. Now, different modalities coming into picture, trying to manipulate my qubit and trying to get an output based on quantum postulates. Why do I need Groover? For 2 power 2, 2 power 4, 2 power 8, I don't need Groover. Okay, slowly I can manage with my system only. The space is getting increased. Large space, huge amount of time, big numbers. That is where I actually want Groover. For example, trying to break a symmetry key. In this case, we have the length is 100. The space that I'm trying to work out with the strings is 100. How many states are possible in a quantum computer? 2 power 100. Can I just write 2 power 100 here? I think this is what 2 power 100 is. Dot, 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 dot. These many states are there. In these many states, I should actually look out for the value. I should actually look out for my optimized value out of the search space. Everything I'm talking about is search space because we're talking about searching algorithm. Okay? In this search space. If I'm talking about source, I'm going to talk about the factorization of it. Correct. Now, this much of state vector is being generated. This is a state vector being generated. Once you get number of states, once you initiate n, once you get number of states, a state vector will be generated, which is hidden from the user. Why am I specifically emphasizing on some things which are hidden, some things which are visible, is because tomorrow we should not take the power of quantum computer for granted. Everything is there only, I can work on it. No, you try to work, it will change. Let's manipulate and get immediately speed ups. We know so much already. This is what we get to a point. No, we know so much. I can actually visualize. I know what kind of data I'm giving. I know how many states are being generated. I can simply try to manipulate. Like your normal machine learning data which is generated. I take all the parameters. I'll do my analysis, Fourier transformation, and I'll get the answer. But in this case, even if we have done so much, something else underlying is changing. What is that? The randomness. That is the randomness. That is power. At the same time, there is a caution for us also. The catch is practically no access to the values in vector space because the complete space vector is invisible. The complete space vector is invisible. Once you're getting out, you get out in the form of magnitude. But the values are invisible. Correct. So where do I start? Where do I start? I'll have a single component that I want to work with. I'll have a key. I'll assume that this is what it is. There's a formula again there, but I'll assume this is what I want to. Component corresponds to the answer to the question you care about. What is the question that I care about? A huge search space, trying to find a optimized value in that huge search space. So I'm going to focus on this only. This is the second part of it. Amplifying the probability of getting this again and again. 25% is already there. No, this is getting 25% of the times. The probability of getting this value is higher. So that means my coordinate system is slowly trying to get to a value which is my key. This is what it is. Here's where Brewer's helps. Gives the insight into how this looks. So this is your string, 25% of probability of getting this. As of now, you got something in the length of 18%, 19%, 20, 21. So these repetitions are there, no? This is the last part of Brewer's algorithm. So what is that we need to do? Everything Brewer has done. What is that we need to do? So I told state vector is abstracted from you. That is, it is invisible. I told no matter how much you initiate, at the end of the day, randomness is there. It will change. So what is there in my hands is nothing but the number of repetitions I can make towards getting that specific value. Two things: number of repetitions, finding the sum of squares, and then the angle at which I have to rotate. This is what I'm only bothered about on Brewer's. Other than that, nothing is there in my hands. Initialize the state vector, equal balance of probability will come across all the possible outcomes. This is what I will do in the first place. We'll start, see, we are fair enough, okay? We give everything a fair chance. We did not start with bias. There is no bias induced, which is a beautiful thing of quantum. There is no bias induced. Everything will have a fair chance. Next step, we have come to the end of it. One of these outcomes is the secret key searching for. We don't know what is the secret key, correct? State vector will push set of values at a certain probability, and then you realize that, acha, I'm going to flip this. Oh, I told you, right? Once you know this is what it is true, 1 is true. That means K is there, this is what it is, you get true. Immediately the quantum, what this is in classical, immediately in quantum, what it will see? I will flip. I will immediately flip. Because at the end of the day, I'm doing x square, no? Positive I'm getting. So this is the final step of Brewer. I will take a value. If the value or the probability of getting that bit string is 25% higher than all that, that is my key. Immediately I'll flip the sign. That is how I, as a quantum computer, know this is the key. I will not tell you, but I'll know. Once you measure only, I will collapse. Otherwise, I'll keep on in the probability for you. Sometimes you might skip also. Sometimes, if people are like me, what they're going to do, they're not going to stop here. Flip and go here. That is where keep the steps very close to your algorithm. If it is 800, keep it around 804, 805, 810. Don't go drastically more. This is very important. Correct. This finally, tool is available to flip the sign of the state vector at that coordinate. What is there in my hands? I told you, I don't have the hardware in my hands. I don't know the randomness. The state vector table is invisible to me. What is there in my hands? My hands, all I have is to flip the sign. Whenever my operator, that gate, had two other gates, which Diksha will tell you, whenever it gives you true, I will immediately flip the sign of the bit string. That means I know this is the key. From then, as an algorithm, I am going to start working on getting nearer to that. I'm going to start working nearer to that. That is how my probability of having the key increases. So now this is very important. Probability mass, then what happens? The probability mass slowly starts to concentrate over that key value. Quantum computers works with probabilities. When I know 25% of probability is here, my mass should be concentrated on that. My angle should be moving towards that coordinate system, towards that axis, alignment of that axis. So finally, what is the secret ingredient in Brewer? If there is one takeaway from this session, what is the secret ingredient? Flipping is a secret ingredient. That means I know this is true. Immediately I'm going to flip. Once I flipped, I'm going to start calculating the sum of squares of the axis, and then I'm going to get the theta, which is tilting towards it. When I calculate root over x square plus y square, I'm actually changing my coordinates. When I'm trying to calculate the theta, I'm actually changing the angle. We work in both amplitude and phase. Amplitude and phase. These are the type of problems. Okay, verifying is hard. Remember, Grover's algorithm is applied to problems which have solutions. But to verify the solution in a given amount of time and space is something that we use Grover's for. It is not those NP hard consciousness problems that we are working on. It is solvable only. Can you recap this example? How many of you can recap this example? Just to close off this. We have a function. We have a value which is going into a function. If that value is meeting my value, that is a key value, secret key, it is true. Otherwise, it is false. That same classical operator, quantum operator. Classical operator means classical gates. Quantum operator means quantum gates. Which gates you are going to choose? Diksha, we are going to tell you. For this Grover algorithm, which gates that we are going to choose. That's all. For Shor's, which gates that you are going to choose. For Dutch algorithm, which gates that you are going to choose. At the end of the day, it is all about gates manipulation. We are in that level today. So integer, the binary representation, give to the quantum algorithm, and then you get an outcome. When that is what a solution you are looking for, you flip it. If it is not a solution, quantum will not flip it. Once it flips a set of values, it is going to do the square of those values. See, it is 1, no? That means this is what we are looking for. The quantum gate immediately flips the sign at that bit string. If it is 0, it will not flip. That means the probability of getting it is decreasing. Initially, no bias. We started from ground level. Then as we move on, once a flip occurs, then we are going to take the probabilities of it. Linear operations. Goal is to align in the secret key grid. That is the final goal. The final goal is to align towards this. Now, there is this other thing also. You can ask me, Gopika, from the very beginning, you're concentrated on this axis, this key. How do you know? I'm not assuming I know. I'm saying that what if it is on this axis? What if this is my end point? How do I try to go towards it? It can be anywhere. How do I try to go towards this? What Grover's will tell me. Okay, visualization purpose finally over. 3D, 2D, the same thing. 3D, 2D visualization I have shown. Two things you calculate. I told you, right? Angle you calculate, and the sum of squares, root of sum of squares you calculate, and then you do the dot product for both of them. And this is that we will get at the end of the day. This root n. This root n is the cosine angle. If you are working on this side also, you get the same angle. Usually for any kind of measurements which are worked in the unit radians, theta is generalized to 1 by root n. Otherwise, for most of it, it is sine theta is equal to 1 by root n when n is equal to 100 in this case. Large space we are talking about. Sorry, ma. Yes. Okay, maybe I didn't get that. Yes, sorry. Yeah. I half the times I didn't find those numbers, alphabets. Okay, the focus, yes. The final focus is upon this. The final focus is upon this we are going to make. Where do we actually rotate this angle to? I told you initially there is no bias. We start perpendicularly, diagonally only. Slowly, 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 we are going to move towards where we want. Okay. The same thing I have repeated. So we need to flip and then we need to figure out how many repetitions that should be. In this case of n equal to 100, in this case we've got 804 repetitions when we have worked out Qiskit only, same thing. Number of repetitions, and those are repetitions, right? From here, the angle. In geometry, the beauty of geometry is every time there is shift of angle, it is 2 of theta. You need not do step up by 1. You can do step by 2 into theta, the initial angle. So it will generally go and come here. Repetitions, pi by 2 by 2 theta in this case. You get the number here. I think I included that. Yes. You need to move towards this number, whatever number that you're getting. In the next slide, the number is here. 804.242. These are all done by Qiskit only, nothing that we can do. Even in the afternoon, you can just execute it. Towards that, you need to try to move. So this is at 352. This angle, okay. 804 repetitions is going to take for n equal to 100 to get that particular number. At repetition 352, this is the angle that you're going to find. Slowly, slowly, it has to move towards this. That is invisible, okay, but still shown, but that is invisible. The state vector manipulation, that is called invisible. The probability of occurring the particular key is 99.999 at 804th repetition. 804.395 something has given, no? At 804th repetition, the probability of getting that key is this much. I think it is good enough on current quantum computers. Are we sure? This is what we are looking for? Are we sure this is what we are looking for? Quickly can be verified. Remember, we have a gate, set of gates, which Diksha will tell you. Send this to the gate. If it flips, good. Not, it's not. What if it is not, Gopika? I've just got 10 minutes of quantum computer access. I've exhausted. What if it is not? Borrow the access from your colleague and try to do the same thing again. That is what you're going to do at this point in time. You need to again sample it. That's the worst case. The worst, you have best case, worst case for every other. Worst case is you need to repeat the complete thing. That is where we are. Okay. Thanks to Love Groover, part to do in pursuit implementation. I think Diksha will take it forward from here. Thank you. Thank you. There's one more slide I have put. Thanks to Love Groover and lovely audience. Thank you. Thank you. Tea break. Yeah, please. Krantikarans are waving from there continuously. It is again. That's all. Flip and the angle. Amplitude and phase. Amplitude and phase. These are physics people. There are no other, that's what I was asking. There are no other algorithms that we can actually compare it with that run on a quantum computer for search. Unstructured data at quadratic speed. The theory is not so strong. Maybe some have come, they didn't reach to that level. Like Shor's.
There are many manipulations of Grover's algorithm, but not as good as the Love Grover.
So manipulations have taken the foundation from Grover's? Grover's, okay. Changed what? Which has
Just based on the problem, what they want to change, whatever the functionality, whatever unitary form is there.
Okay.
Just a little bit change into that.
The UFU to gates, that's
Yeah,
all. Okay.
depends on the problem. Nothing much, but the base thing is this Grover's algorithm. So that's why we generally focus on Grover's algorithm.
Okay.
Everything come up from there.
Yeah, that's like brute force is the base, and all other optimization algorithms can come from there. Thank you. Thank you.
Please.
Madam.
మ్యాచింగ్ మేడం నేను ఆరెంజ్ వేసుకుంటాను తెలుసా మీకు మ్యాచింగ్
Dr. Kusuma madam. Join me.
Madam.
Thank you. Please.
త్వరగా
Thank you. Thank you. Thank you. నేను చేస్తాను, నేను దీన్ని చేస్తాను. ఫోల్డ్ చేస్తాను.
If needed, I present in middle. Okay. So, first of all, thank you, Gopika, for a wonderful talk in the morning on Grover's algorithm. Audio fine? Okay. So she gave a lot of visualization. I think that was very, very useful and needed for understanding this complicated Grover's algorithm. Now, again, as we know, quantum is all about physics and maths. So we'll dive deep into the mathematics and the equations which govern the, all the operators and, rotations that we talked about. So just waiting for slide to start. Yep. Okay. So we are all like coming from computer science perspective. So we are trying to think about yeah. Okay, thank you so much. So we are all coming from computer science perspective. We are thinking about search algorithms. So Gopika already touched upon this. We have something like structured and unstructured search. So I'll just tell you a very simple example that if you want to find, say, number 13, this is a structured data that we have. This is ordered in, say, increasing. This is actually an easier problem to solve. We realize this. We can also do binary search on this. But what would be more tough is if we have such a data which has no structure as such. So most of our data today is actually unstructured. So that's why this problem becomes very important to be addressed. And obviously, when we are talking about complex problems, we are always trying to go to quantum and try to see what quantum will give us for, if there is any advantage or if it's able to, solve that complex problem for us. And very rightfully already touched upon is that we wouldn't actually know this order. This is just an example that I gave. But the idea is that we would only know that what we are looking for, and that we would only know using an oracle, which she already talked about. So you have some black box function that you can send your data and see if it's true or false. So what I will do in this slide now is dive deep into what this black box would look like, dive deep into what the Grover's amplitude amplification actually looks like in terms of just mathematical perspective. And it was great to, first of all, start off with a visual perspective so that, we guys can now see what we are looking in terms of the maths. Okay. All good? Okay. I'll just keep this for now. Let's just go to the slides. Thank you. So yeah, I will just again talk a bit about quantum search, then about Grover's iteration, which is the main key thing that Gopika was talking about. It has the effect of moving towards the solution state after multiple times that we apply the Grover's iteration. We'll talk about quantum oracle. Sorry. Then we'll talk about amplitude amplification, and there is so there is one specific example. Okay. Thank you. So all of you online, no worries. We'll start from start. Yeah. So I was just saying that my master's thesis was on Grover's algorithm itself. So I would also take the opportunity to talk about a specific oracle design, which I did in my master's, which was for the problem of finding good match vectors. So the good point here is that we will have some time to dive deep into, what an Oracle design would look like and what this black box could actually look like. What combination of gates would actually result into a solution to the problem, like example, finding good match vectors. And then we'll conclude. So yes, Grover's algorithm is a pioneering algorithm for unstructured data set given by Love Grover, which we already talked about a bit. It's a quadratic speedup. Why it's a quadratic speedup, we'll dive deep into that. It has a lot of applications in cryptography, optimization, AI, especially because these problems rely on, say, efficient searching of large data sets. So this is the core problem which Grovers will solve, searching large data sets, especially unstructured data sets, like only unstructured data sets. And it was great to see in previous talks about, quantum adversary and the symmetric encryption that we talked about. So yes, if we have today fault tolerant quantum computer and we have, say, 1,000 or more qubits, there would be times where, we will start breaking AES codes, symmetric encryption all. So Grovers has vast potential, and this is also the reason why people got excited in this field, because this algorithm was given long back, but they always, why we are fighting for this race of developing a quantum computer is to see when we actually implement this algorithm and see its, effects in vast fields that we use today every day, like optimization, AI, cryptography. Okay, so just a pictorial representation of one of quantum computer, Google's superconducting quantum computer. So just to give you that, okay, this is how one quantum computer looks like. Actual chip is in the bottom, and these are all dilution filters to just cool the chip and make sure that there is as little as temperature, so that it's not also not interacting much with the environment. As we know, it will start decoring. Okay. Okay. So I think we have discussed a bit, but I'll just touch upon it and continue more, add more details to what we are talking here. So a classical search would take order of n. So we know that if we classically, let's just forget the structured data for now. So classically, if you want to search something through a data, worst case, it would be order of n. Let's say our item of interest is 13 only, but it's at the last. So worst case would be that you travel through the whole array and it would be order of n classically. But Grover's search would have a approximation that we can do it in order of root n. So this is the main reason of interest. Yeah. So I think she also talked about some complexity. So this is one graph we can use to just see how advantageous Grover's could be in a search space of size n. So this is a search space of, say, 5, but n equals to 5. So this is just a general diagram. Time complexity. Okay. And please, this is going to be very detailed here forth. So please keep asking doubts. And this is a very important algorithm. And it also tells us that, if there are 3 experts trying to deliver just one topic, so it is complicated, right? So I'll give you a first high level overview. I think she has already touched upon these keywords. So it's good for me to, give you now the nuts and bolts of these. So first you have to initialize. So state preparation is always there. And then we have equal superposition. I think this you might have seen yesterday, equal superposition. Then these are the 2 main things in Grover's, the Oracle application and the diffusion operator. And then you do measurement. But now we'll see, and this we repeat iteratively to move towards the solution. So that was what Gopika was trying to say before, that we are trying to move towards the solution. The number of times you repeat the Grover's iteration is how you move towards the solution. Okay, so this is a very nice figure to just, we'll start filling in these boxes. So first you do the equal superposition, then you have this G black box for now, Grover's iteration, which we have to repeat order of root n times, right? So this is a simplified diagram. Okay. Now let's just dive a little deep into what are the core procedure for this initialization superposition. So yes, initialization we prepare in state 0, which is already the case. So that's good for us. Then we apply those Hadamard's on n qubits, right? And these are the n qubits we're talking about. There is an extra Oracle workspace which we need. that depends on your problem. So if you have a simple problem, your Oracle workspace could be small and that would require lesser qubits. If your problem is much larger, you will require a larger Oracle workspace. So we'll again see more detail into this. But yes, so you have this state psi after equal superposition, which would look like this. Okay. So this state effectively represents the entire search space. We start off with just equal superposition. And just a small question here. Can you guess the quantum circuit for initializing n qubits to this and applying Hadamard gates to each of these? It's simple. It's just the... Anyone wants to guess maybe? I already showed it, but okay. So it's just this part I'm talking about. That's it. So this is Hadamard on each of the n qubits. This is used to get this equal superposition. So that was what I was asking. Can you guess the quantum circuit? Now I'm trying to, make you think like an algorithm scientist or something, like, how do you design quantum circuits, or how do you, which gates should you use for such things? So as we know, basic gates are the core thing, like X, Y, Z, Hadamard, everything. So, but how do you design? How do you know that this gate is what we need? So, okay, Hadamard is used for initialization. That's there. Right. And next is the Grover's iteration. So I think already seen this equation in a similar form before, but okay. This is a general one. So Grover's iteration is this core subroutine. So why I showed you G repeating n order to the root n times is because we want to now see what is inside that G black box, right? So let's say that we have m number of solutions and n is our space. So your repetition of Grover's would be approximately this. So as already said that, if you repeat more times, it would go away from the solution after a point. So this is a approximation that for your example or any example, you should calculate at your end and see, so that you know that you're not doing over repetition as well. Okay. So there is this Oracle application. So now I'm breaking down what is there inside this G. There is Oracle application and there is diffusion operator. So let's look at the Oracle first. So Oracle identifies the state X. So for our solutions, let's do one thing. Let's start breaking down the black box as such. So there is something G, we don't know, but this would have something would have something which would look like an Oracle application, let's say O, and there would be something else which would look like a diffusion. So this Oracle application is what identifies our state. So as we talked about in hard problems, NP hard problems, but the good part is we can verify if that's our solution. So this is what our Oracle will actually do. And this is where the designing aspect comes in. So whichever problem you're trying to solve, you have to design your Oracle based on that problem. So then you can, take the full advantage of Grover's algorithm. Okay. Okay. And then there is the diffusion operator. This is defined and this is fixed. So this amplifies the amplitude of marked states. So from this we know some states are marked. Marked means the states of our interest, which is actually solution states that we're talking about. And then this is a fixed operator, which is defined as this, where psi is the equal superposition. Okay. So I'll again try to break this down. Which is next. Wait, sorry. So this is the diffusion operator D, which is fixed and which will look like this. So we talked about psi being the equal superposition. So when you plug in psi from our equal superposition, our diffusion operator would look like this. Okay. So again, can you guess the quantum circuit for diffusion operator showing Hadamard gates surrounding a controlled phase gate? This is a difficult one, but if anyone wants to try, please. I want to see how you guys are able to think on quantum circuits now. It's just circuits like gates, but still. Would anyone like to guess the quantum circuit for a diffusion operator? It's a fixed operator and it will also have Hadamard gates because, as I told you, there is equal superposition. Anyone wants to give it a try? Okay, no worries. We'll look at it. So yeah. So now O and D, I'm trying to show what that is. That is the Oracle over there. And why is the Oracle spanning down to the Oracle workspace? Because we need that Oracle workspace to actually implement our Oracle specific to the problem that we are discussing. But your diffusion operator is fixed. So that is only applying on the n qubits that we are in discussion for, right? And this is the whole G, which we have to keep repeating. This is your G, fully visible there. And this iteration, this is one iteration of Grover that we repeat. So when we talk about repeating something order of approximately root n, so this is what we are repeating. Again, we'll see more detail. But before we go there, I think we'll just talk a bit about this thing called quantum oracle, quantum oracle. So what is this oracle? Oracle is actually a black box. Yes, it is a black box. Like this is a black box. You don't know what this is doing, but you know its expectation, like functionality expectation. You know what this oracle is expected to do. You know what the diffusion operator is expected to do. So when you're talking about this oracle design, this is the topic that we're discussing here, oracle design. So we want to actually now very important things, you know, phase kickback. Then you talk about even the so here the input would be your minus state, which you can see, and there would also be your X state, and the expected output, this is your phase kickback, and your expected output would be that when it's a solution, you want to have that minus, and when it's not a solution, you want to just keep it as it is. Okay, X. I think it's written there, but okay. Minus, not a solution. And this is this minus. This is what is of interest, phase kickback for solution. Okay. So any questions, please. Okay. Things will keep getting more tricky. So amplitude amplification. So now we are coming back to Grover's. I just So two important concepts which we talked about. One was Oracle black box, and another is phase kickback. Right. Now coming back to Grover's algorithm, which is this Grover's iteration. There are two steps here: amplitude amplification, then the diffusion operator. So we'll see more detail into this. Okay, some theory, but we'll just skip that. Let's look at some maths. Yes. So there is a geometric interpretation. I think there was good thing about the previous lecture was that we saw a lot of geometric interpretation, so that now we can see why that is how we can visualize this Grover's algorithm. So the good part of Grover's is that there is a visualization that helps us think about what's actually happening. So I talked one thing that there are n. So in this previous example, I was saying only one quantity of interest, but your quantity of interest could be higher. That is m. M items are solution. So your non-solution items would be n minus m. So now you're trying to define this state psi such that it's a superposition of your non-solution states and solution states. So S0 over here are non-solution states. S1 over here are solution states. Okay. Let's look at a diagram actually if we have here. 1 second. Yeah. So yep. All good?
Yes.
Okay. So alpha is your non-solution state, S0 which I was talking about. Beta is your solution state. The idea here is that you start off with something like psi, which is your whole space that we are defining, including the solution and non-solution. Then you do some operation, which is this oracle, that actually rotates this. If this is at theta by 2, it rotates around non-solution state down. And then again it rotates around itself. This O of, after reaching here, you rotate around psi again to get the actual operation of G over psi, which is your Grover's iteration. So what I'm trying to say here is that this is what you do first. You make sure that you identify the state that you are of interest, but you map it with a minus sign, phase kickback. You bring it down, but then again you have this fixed operator, diffusion operator, which actually pushes you towards the solution state. So the beta over here, or S1, is the solution state that you're trying to move towards. We already saw that a while back in the previous lecture, but okay. Yeah, so oracle is a reflection about S0 axis. S0 is your non-solution state, and it flips the phase of the solution states, S1 components only, while leaving the non-solution states unchanged. Why it would do that? Because we are using something like this. So only flipping the phase for the solution state, and yeah, not doing anything for non-solution state. Correct. And then you have the diffusion operator, which is fixed, and it reflects about the initial state psi. So this is your initial state psi. So I'll just try to again draw it out. If anyone has doubt, please ask, please. So this is your non-solution state, alpha, beta, your solution state. So you start off with something like psi. And this, just we are saying it's at some theta by 2. The idea here is you reflect it around your non-solution state, get this over here. Yeah, get this over here by applying your O on psi. So it rotates, it goes down by theta by 2. But then after this, you do the diffusion operator, which actually rotates this O of psi with this axis. So this is theta. So rotate again with this axis, and we are moving towards. So the idea is to move towards this. So this was your initial state. As you do these operators, intuition is, so this is 1 G of, psi. So the intuition is these, say G square. So these operators keep applying. So you move towards the solution state. And when you do the measurement, you're left only in the solution state. So that is the main intuition over here. So this angle will depend on how you, what problem you are doing. It's which angle, sorry ma'am? Okay.
Here, O of psi, we are moving towards G of psi.
Yeah, one second. This angle? Oh,
G of psi.
so This is fixed. This is fixed in the sense that this state psi is what we rotate around, and that is why the diffusion operator is fixed.
That is theta.
The angle is fixed. That's what
Angle
she
is-
is.
Okay, wait. Okay, I'll just break it down. So this psi, based on your solution and non-solution, how your vector space looks like, it would be some angle theta by 2. Yes, this angle based on your definition of psi would be fixed. And then you would keep rotating. So now each rotation would first put it by theta by 2 below the non-solution, and then another theta. So this is theta, you rotate theta. So this is actually theta. This whole angle. This is theta. So this angle would be fixed, but your operation would always keep pushing you towards. And why would that be the case? Because once you reached here, now you would flip it against this. So initially you started with theta by 2. Then you would have 3 theta by 2. So you this one now will be your starting. Then this you will flip around this. So it will go down. And after it goes down, you would flip around this. Oh, sorry, you would flip around this only. Yeah, sorry, my bad. Only flip around this. So again, you move towards. Okay.
Here, psi is there.
Ha.
And you have flipped it.
Ha.
So theta. And again, 2 theta. Is it right? I think it is 2 theta. From O of psi to G of psi, is it 2 theta?
Yes, 2 theta. Yes.
2 theta. How much
Yes.
we are going now?
Yeah. That is 2 theta. Yes. Perfect.
So by the first part itself, it's non-solution. Then why again still moving down? We can directly pick from there.
Great question. So the idea here is great question. So she asked that why do you want to move down to go up? Right? That is because we have something like phase kickback. So it is easier for us to employ this oracle, which actually applies this minus sign to our solution state. So what we are doing is we are actually first giving minus to solution state. And that helps us, like it's like a boomerang, trying to go back to go ahead. So you're going back so that you can now flip it around your psi and go towards the solution.
Conforming. One way.
Sorry?
Confirmation.
Ha.
Means we are moving
You are
towards the
coming down
non-solution
means
state and moving
that
towards
value you know. Means if the algorithm reaches that value, you are telling that this algorithm is by giving these angles, it is reaching the correct, it is doing correct iterations. So by increasing by reaching the non-state down below, and again it is flipping means these iterations will be going smoothly towards correct phase and ultimately reach for the solution.
Perfect. Yes, that is what it is. Yes.
Am I correct?
Yes. That is how it is. Let's do one thing. I got a good photo at the end. Okay. So the idea was that this is our solution state. So now we are looking at the oracle and the amplification. Okay. So this is our solution state. You first marked it minus. You marked it with minus. You identified it using your phase kickback trick, and then you amplified it. So it became double. Yes, that is the idea. Right? Yeah. Thank you for questions. Very useful.
The second iteration,
Wait. So that's what. This is the oracle and the amplification. So as I was saying, O and D, diffusion and amplification is actually same meaning. Amplification is diffusion operator. So the second one, amplification, is the diffusion operator. And oracle with amplification is one Grover's iteration, and you repeat the whole Grover's iteration for order of root n times. Does that help? Okay.
reach to G.
Okay. To repeat it again. To repeat the oracle, again you want to mark your solution state, again you want to go down, then again go up.
ఆ స్టేజెస్ మళ్ళీ కింద
Please.
Now we have reached for the first iteration, we have reached G of psi. And now the angle is 3 theta by 2.
Okay.
ఇక్కడ quadratic
Yes.
Now, again, for 3 theta by 2, we'll be moving in the towards the non-supersonic state. And again, we'll be going 2 into 3 theta by 2, means 3 theta towards the solution
Yeah.
state.
I'll just show you a little more detail on this theta discussion. Can you help me present? I'm presenting. Present.
మళ్ళీ ఆంప్లిట్యూడ్ తో దాటి ముందుకు వెళ్ళింది మీకు ఇది
Three theta by 2 ನಾನು అనుకుంటున్నాను. 3 theta by 2 తో కిందకి వెళ్తుంది.
Yes.
అంటే 3 theta
Yes.
యాంగిల్స్ మార్చుకుంటూ
We'll see. Thank you. Thank you for these questions and interactions, and thank you, sir, for making sure that people are understanding. So this is the setup that we have. This is our state psi that it looks like. Okay. Now we'll see the detail on the angle. So this is from the Nelson and Chong book, which is the famous book and probably the god book for quantum computing. So yeah, this is how your G. Yeah, but are we good?
Yes.
Okay. Everything is good, right? Okay. So this is what G of psi would look like. 3 theta by 2. 3 theta by 2. Why? Because you're measuring from this. This is your x-axis. So from here you're saying 3 theta by 2. Okay. And repeatedly doing this, you're right. 2k plus 1 by 2 theta. So this is what I think someone was saying 5 theta by 2 and yeah, 7 theta by 2. So that is what it will do. So that is G to the power k. So the idea is you will repeatedly do this. G, K, psi. This would lead us, and this approximation, how many times you want to do K, is what Gopika was also Gopika was also talking about, that if you don't want to do this K more times, you want to have an estimate for this and apply that many times only. So finally the thing is, everything that's happening here, you don't know anything about it until you measure. This is another thing I want to again keep hammering. So the point is, until you measure, you have no idea. So if you measure wrong, like say your K was supposed to be 10 and you measured after 20, you don't know where you are. Only after measuring you would know. And same thing if you do it before 5. So you are close to solution, but it may not be the case. So this is why there is this also very nice, I think they have done an approximation and given an estimate for theta. Is this here? Yeah. So where theta is real number in the range 0 to pi by 2, theta is from 0 to pi by 2. So sine theta by 2. So this is like theta would look like sine inverse this value. Right. Okay. So again here m is the number of solutions that we have. If m is 1, if you're only searching 1 and say 5, like if we had this, let's take 3 only. So if n equals to 3, you're searching say 21 and 13, you're searching this 13, and n equals to 3 in this case, m equals to 1, you can approximation may or may not happen. You can check the condition, but yes, you can plug in the value and check. Okay. Okay. Let me see if there's anything else for me to show you here. Okay. Yeah. Yeah. So this is the another just a range for sine theta. So actually you don't want sine theta by 2 also, like you want it to be less than theta by, like approximation that theta by 2 will be always greater than sine theta by 2. You are using that to get an number of iteration approximations. So the approximation that we saw, pi by 4 root over n by m. When m equals to 1, it will become pi by 4 root over n. When m is 1, that is what I think we saw when Gopika was showing that estimate. And now this is for general case where m could be the number of solutions and n is the total space that you were working in. Okay. So I think anything else? So this is the same figure. I think I'll stop presenting from here. We'll go back to the slides. Thank you. Okay, perfect. So great that you guys are so much involved, because these are the only two key things that we need to understand. We are keep hammering it so that there is this grasp on the concept. Okay. So right, there is the Oracle diffusion operator, which is also the amplification. Yeah, also called the amplification. That's why we have this amplitude amplification that we're talking about. Okay. And right. This equation we already saw. Your state psi would look like this. And yeah, I mean, normally why this a small angle approximation we use is because your solution state n would be very high, say 100, 10,000, and m would be less. So here n and m are close actually. That's why I said you may not be able to do the approximation. But in general case, any application that we're doing, probably the order of n would be what? It would be, say, you're searching a data set. So data set could be like, say, 100K. And the solution that you're looking for is probably just 10. So you're just looking for 10 out of 100K. That's why we can use the small angle approximation and get an estimate for the number of iterations and the theta as well. Okay. Next. Yeah. So Grover's operator is actually a rotation. You can see eventually what you're doing is you're doing some rotation. And to get this rotation, there is a step that you first rotate around the non-solution state and then you rotate around this, you get this. Okay. And this repeated application of G is what will help you go closer to the solution state. We have already discussed this with high probability, and we saw the probability also in last class where she said there's 99% chance of getting it. So there is actually this high probability, which is why people are so much interested in Grovers, and which is why when we have a fault tolerant computer, we are all threat for the cyber threats and all, because Grovers is going to work for sure. That is the thing that we are also running for. So why it's very important to discuss about post-quantum cryptography, quantum safe and all, because before this happens, there's a race of making quantum computers, but before people make fault-tolerant quantum computers, you want to be safe also from its adversaries, like the threats from quantum. Okay, next. Yeah. So let's dive deep into now what an oracle could probably look like. I will try to give you an insight into the actual oracle for this finding good match vectors. So this was my master's thesis topic, and thanks to my professor Sarah Crook from University of Glasgow, we worked on this together. So this was something which I was very excited to work upon, because it helps you see more in detail of what a Grover's algorithm is and how actually you can employ it to your use case. So the idea is I'm giving you Grover's algorithm, everybody can read that. But how do you use it for your use case? Like a prof or someone would want to use it for, say, medical purpose or some other data sets or some, I will show you one example that we have. So finding some good match vectors. So, right. So what is this good match vectors that I'm talking about? So the idea here is that anything that we are trying to, classify in normal machine learning, or anything that we are trying to, search. How do you do that? You say, I said I want to search for 13, but I want to also make sure that I'm actually getting 13, in the sense that I want to see if 12 and 13, how close they are. It also means that if 13 is what I want, but if it's say 100, and maybe our answer after whatever we are using, machine learning, quantum machine learning or Grovers, if the answer I'm getting is 100, but I want to verify later if it's close to what I was looking for, this is not the case, but okay, this is the case. So the idea here is, once you have overlap between the quantity of interest, let's say 13. So here I've defined, identify the vectors, predefined target vector. Okay, so the target vector is psi in this case. So your predefined vector is psi. This is what we want. So this psi in our classical example is 13. This in quantum example. So again, when you talk about any quantum state, you have to map it to your problem statement. So you have to define psi in terms of whatever problem statement you want. And say the phi I is the, space in which you're searching. So just breaking this down, what this means is 5i is all the, elements in your unstructured data set. So 200, 113, like that. So this is what 5i is. And when, example, we are doing this inner product, we remember this inner product. So when this inner product has a very high value, say above some threshold, this is completely mathematical in the sense that this is a general problem. We can, You can define more about this threshold. You can define more properties about, say, your psi I and your quantity of interest as well. So the reason why we took such a problem was that we want to have a general estimate, and this has many applications. This just solving this using, say, classical computers, it's becoming more complex. But why we employed Grovers is to get the advantage of order of root n. So if we are successful in designing an oracle which actually does this task, and then we give this oracle to Grovers, the whole Grovers iteration, we'll get an advantage with the order of root n. So now our problem is, initially our problem was what? That oracle would verify the solution, right? Whether it is our solution, yes. If it's not a solution, no. That oracle I'm not talking about. Now I'm trying to create another oracle which will actually do this task. And once you create that oracle, so you are able to use the Grovers and solve your problem of interest. So the idea is, oracle is something which you have to design problem specific. Oracle design is problem specific. So that's why I think we are talking about if there are some other searches and all. So there are people who are very smart and have got very indigenous ways of this oracle design. And that's what I think we talked about, that there are variations of Grovers. Some variations of Grovers are there which are again just employing the same idea. And let's look into this now. Okay. So again, actually we would have an oracle which would want to also use the phase flip thing. But main idea would also be to design this oracle such that for our problem. Okay. So before I get into this, let's have a very small activity. Let's look at something like swap test. So what is swap test? What is swap test? This is swap test. This is a simple quantum circuit. This actually quantum circuit, we should you should now be able to go through after each gate how the state changes, right? I will just show you the math for once, but I will just want to tell you that this swap test actually gives an estimate for overlap between two unknown quantum states. So these are our two unknown quantum states. There is an overlap, which is the inner product, and using this swap test, which this setup 0, psi and phi I, we get an estimate after measurement on the first qubit. We get an estimate for the overlap between these two states. So if you ask me, I think some professor was asking me that we need to give some questions. So my question would be to solve this and check that why this is the case. How do you get the overlap? But this would be a hand calculation. So let me just give you an intuition for it, and then maybe if you are that interested, you should go back and solve for it. So this is 0, psi. This is your phi I. Okay. Time. Okay. So this is our Hadamard. Okay. So can someone at least identify the middle gate over here, please? Okay, CC0, and it's also called the. Perfect. Thank you so much. Yes. So this is the control. So why I asked that is, if you realize your gates are the same, it's just how you use the gates. Okay. And now you measure. Right. So this would remain same, 0, psi, phi. After this, what would happen is Hadamard would apply on the 0 state. Right, and your other states would remain same. Then you apply C0. C0 would apply on this state. So it would be CC0, Toffoli gate, on this whole thing. And then again you apply the Hadamard on the first one. So I will just, for sake of my ease, I'll apply Hadamard here. So the idea is you apply Hadamard on the first one, then you apply the CC0 gate, then you again Hadamard on the first qubit. Okay. So what that means is Hadamard, tensor I. I hope you remember first class we were talking about tensors. So the idea is when you write like this Hadamard, tensor I. So you are saying that identity on second and third qubit and Hadamard on the first one. So this notion is also important to write. So again here Hadamard, I would like to specify it would be Hadamard tensor I. And what is the meaning of this tensor I? It's identity. There's nothing happening in this. Perfect. Okay. So one should actually solve this, and solve this means you will get a, once you expand this, you will get some equation. Then you have to find the measurement probability of state 0. So not state 0 of first qubit. Then you will find the probability of, say, first qubit being in 0. What is the probability? So this would be the actual question. Probability of 1. What would be this probability? So actually, you'll realize if you find 1, you know the other one, because one probability of 0 plus probability of 1 is 1. Yeah. Yes. So in this probability, actually, there is a relation which brings back our inner product that we're talking about, right? So this is a state psi, state phi, right? And mathematically, I have expanded more things, but okay. This is actually the probability. Probability of 1 would look something like this. And the complexity, single swap test, complexity for that is this, but it's okay. We need not get more detail into that. So this is our key component. And the reason why we are using something like swap test, it's a very, very famous test. When people talk about quantum machine learning, this is the go-to thing that we do. But it depends on what your initial states are. So basically, this states someone might specify a new swap test for some other task, and or as I am employing for my task, so which is for psi. Any doubts? Okay. Okay. So now this is where it gets tricky. Now designing the oracle, and we know that okay, this swap test would help me get some estimate of the probability. Could be useful for designing the oracle of interest that oracle would say. So the idea is now, when we talk about this being greater than some threshold, so oracle when it's greater than the threshold, you want oracle to say yes, and when it's not, you want it to say no. Very similar to being like this is a solution, non-solution, marking this as face flip and other things. So very similar to that. But the idea is, how do you get such an oracle? So this is what my thesis mainly brainstormed on. So there would be some state preparation that you would do. So the state preparation is a very simple thing. I have specified this this step, so that I show you that okay, everything in quantum actually you have to prepare. So you will start off with something, not even this. You will start off with 0, 0, 0. Then you will prepare it to first I 0, 0. Then you will prepare it to psi. Then you will prepare it to phi I. But why I showed the phi I? Because these are your all the space, vector space that you're like your data. Like you have all the solution, non-solution in psi I. And again, I'm using the word solution, non-solution because that's the language which Grover uses. We can interchange that language based on the problem. Okay. So let me again go to a picture directly. So our proposal was that our oracle would look something like this. This is the O oracle that I talked about in Grover's. Diffusion operator is fixed. Okay. So our proposal was to use two things here, where we are using k copies of our data. So if you see, there was some swap test calculation I was talking about. Our proposal said that no, you need k copies. So if you realize, we always talk about complexity. So actually this increases your complexity not time wise but space wise. So you're actually using k copies. Then there is something like conditional psi. The good thing and the bad thing is, I'm trying to define an oracle, but I'm putting an oracle in the middle. Okay. We did that again with Grover's. Grover's had two oracles, oracle and the diffusion operator. This is our oracle for this good match vector case, which would look like this. But again, this conditional sign is what we want to design. So we always do this. Now we want to break down the problem and now get to the core of it. So we use this swap test very indigenously. We said that okay, this would help us get an estimate. But then this is something which we want to do, conditional sign. Right. Okay, in this figure, I'm just asking, so once you measure this, what happens? You're like, I'm showing only measurement on first qubit. What about the other qubits? Am I measuring on other qubits or not? No, yes, on the pictorially, yes, because information will be on this. But the idea is once you measure this, all of this will also like be collapsed. Yeah, and our information lies over here, but yeah. So let's look at this. What now what I will do is there is parallel swap test K copies. I showed you in the figure. Let's again not see more of maths. Let's go for the intuition. Yeah. And conditional sign oracle. So this is something, a separate classical circuit processes that the outcomes from the K parallel swap test, okay, compares the estimated overlap against the threshold and applies phase flip to the corresponding state. So what I'm trying to say here is again that this is nothing but somewhat like a phase flip operator, conditional sign, okay, and this would corresponding state I means whichever state has this high overlap, you want to mark it with this phase. And the last step would be uncomputation, which I'm showing here only for the sake of completeness, because I'm saying I'm starting from this state, so I'm applying a state map. So to get back your so to make sure that your algorithm you uncompute, so you again put a M inverse, so you remove your state psi actually, sorry, phi I, so you uncompute. It's fine. I mean, you need not worry about that for now. Okay, but the idea here is how do you think about this conditional sign then? So mathematically we have problems, right? We think that okay, now this is our problem, we want to think about this. So my task was again to like think how would this conditional sign would look like. So what we did is we actually went to just basic gates. I'll show you conditional sign for 2 copies. So when k equals to 2, but the idea was that we wanted to use something like control Z gate. And this is our swap test. This is our swap test. So if you look at this, this is our, conditional sign that I'm talking about. So let me do one thing. Let me just write it down. So please, any questions, please. I mean, this is not the trivial Grover's, we have come across the trivial thing. Why I'm going into the nuts and bolts to show you how do you design or how do you think about this. Again and the swap again. Pardon me for my lousy and you see the control is going from one copy to the another. So the idea is why we're using multiple copies is because we want to get link between these copies. We want to make sure that the data, what we are looking for or the quantity of interest is actually being like interlinked. No, the idea here is that you're using multiple copies because you want to actually somewhat create correlation between them and then try to get that thing outside, like the data outside. So the whole oracle task is what? The whole oracle task is to tell me if any quantity is greater than this threshold, the overlap is greater than threshold, yes. If it is yes, then good. If it's no, then also like, but you want to do this correctly. So I think you were saying something, but I missed it. So the idea is you want to do this correctly. So once I propose this oracle example, this is not to say that this is right. Actually, this is a proposal. This is just a design. After this, I have to verify. So another second half of my thesis was to just mathematically verify if this is close by to the solution or not. And another thing was to try for multiple copies. So keep repeating, try for another copy. So I just showed you for 2 copies. I want to do it for say general case of k copies. And the intuition was that as you increase the copies, you are actually getting high accuracy in this task that you want to do. So high accuracy means that you are able to, with high accuracy, say that this is above threshold, and when it is yes, it is with high accuracy. When it is no, also with high accuracy. So you don't want to get this wrong, right?
Entire input is taken.
Yeah. So talk about input. This one, na? Yeah, so actually input for swap test was this, but we are using, yes, multiple swap tests, so even multiple inputs have to be given. Yeah. So multiple copies means multiple inputs for each of them. But when you talk about in general, your input is just on the left side. So all of that is your input. Okay. So I think I would like to leave you here, because there is, like, in terms of like my thesis work or in terms of just the Oracle design. So again, one can go and calculate this circuit. You can go through each step and see what actually it's doing, calculate the probability of this qubit, right? And this, again, this is just your Oracle O. So let me do one thing. Let me just go back to where we started, which is Grover's. Perfect. Yes, love Grover. So yeah, this is your Grover's iteration. So what Grover's generally is this, but when you want to use Grover's for your any specific example, you want to design this Oracle such that it does the task that you want. And the task that you want, you define. And then once you define that, you say that, okay, if it's successful, you face flip. If it's not successful, you don't face flip. So that was the main core idea. And your diffusion operator is just like this 0 to 0 and x to minus x, actually. Yeah. So this whole thing is your diffusion operator. So this is fixed. Right. So let's just conclude this so that we can finally, like, after the lunch, I think we'll have some implementation. So the fun part would be there. Yes. So I'll just give some conclusion for my thesis. We employed for, say, k copies. We want to find this k. So again, this is open problem for enthusiastic researchers, that what would be an estimate for the k. Then you want to also compare this approach with classical approaches, in the sense that I talked to you about that, okay, this is some interesting problem, finding good match vectors, but you also have so many very highly smart people who have already proposed some algorithms classically. So you want to make a comparison of, say, space and time complexity. So as of now, this thesis is not available publicly. Otherwise, I could have showed you all the analysis that we have done theoretically, at least. But yes. And again, once someone proposes algorithm, it's always the case of experimentally realizing it. So even realizing Grover's is a task. But then once you have your quantum computers available easily and also like fault tolerant, then you can start experimenting with these things. So the idea is that we are from industry, we are actually now looking at, say, specific problem designs. So we will design them, but we'll also then be experimentally realizing them, such that we know the feasibility of such a design or Oracle or the algorithm that we're talking. And there are very broad applications, optimization and diverse fields for the good match vectors as well as the Grover's. So, sorry, 1 second. Oh yeah, this is for Grover's. There is quadratic speed up. There is you want to construct an efficient quantum Oracle. So this efficient is the keyword. So the idea was that you propose this. Maybe sir will come and propose something else. But then you want to check how efficient that Oracle is doing the task that you want to do. And you have to define all this mathematically. And yes, we dive deep into amplitude amplification, then design of Oracle. I gave an example using the swap test and the problem that I defined in my thesis. And this is what I'd showed before, and I would like to end on this. So this is the great part about Grover's, is you can visually see what's happening. Right? You can visually see that, okay, this is what you want to do. But once you start looking deeper into what the Oracle is, what the amplification is fixed, but what the Oracle is, then the task gets a little tricky and tough. Okay. Thank you so much for listening. Thank you so much. And I think this would be a good segue for lunch. Thank you. And if you have any questions, please do ask. I'm available to answer the questions.
Why it is being called Oracle?
Good question. So that's just how they defined it. So Oracle, black box, these are just interchangeable names. Yeah.
Means some other name we can give it.
Yeah.
Any significance is there?
Oh, you want to see the textbook? Yeah, I'll give you that. Yeah. I think they just named it. They could have named it better, but I think it's just the terminology that they named after. So you want to look at the oh, references slide. Okay. This one only. Okay. The first one, Nelson and Chong. Yeah. Yes.
It is not related with company Oracle.
No. Yes. Good joke. Yeah, no. It's not related to it. No. Oracle is black box. No. Oracle is just a term. Black box. And as we are all, professors and researchers, we want to define the black box. That's why I took some time to dive deep into that, and that's why I really enjoyed Gopika's lecture in the sense that she took the energy for at least explaining everything, geometrically, so that now I can go and fill in some insights into what the actual work would look like. Okay. So this is not available online yet, but okay, if we ever do it, I'll share the link. Okay. Thank you so much.
You don't have your private copy?
I can present it, but that's why my laptop is there. But okay, thank you so much. Thank you.
Okay, now as we have